Right. So, hi everyone. Good morning. I'm Andrzej, and I'd like to talk to you a little bit about statistical dialogue systems, which basically means neural networks in dialogue and related stuff. Um, yeah. So today is going to be basically just like a light introduction. Um, First, I'll start with some organizational stuff, and then we'll move on to basically just like what are dialogue systems and stuff like that. So I hope this works. So first, the organizational stuff. I know it's a little busy, but it's basically all that you need to know for this course, I hope. Basically the lectures are supposed to be every Tuesday at 10:40 in this room. Every other week, starting next week, there's going to be a lab. And I would, if I don't know, tell me if you have any problem with that. I would start with the lecture at 9:50 because the lab never or almost never takes the 45 minutes. So let me know if you have any restriction in the schedule. If not, then that's great, and we can basically do it this way. So we start with the lecture and finish with the lab a little earlier, so you can go early for lunch. Right. So the lecture will be just me waving my hands and talking about theory. Obviously, if you want to, you can always interrupt me and ask. And the labs will be practical exercises, and it will be you implementing a neural dialogue system with a little help of some libraries that we'll provide, but mostly on your own. So you will do the actual hard stuff, let's say. That's and then you'll train it on some data and evaluate it, basically like doing a full experiment over the course of the semester. Starting from the second homework assignment, the first one is slightly unrelated. Okay, so that's the labs, and basically to pass, you need to score over 60% on the written exam. There will be 10 questions covered by the lectures. You can actually see the questions on the website already, even though I might add a few of them. I will let you know, I'll towards the end of the semester, I might update that. These are questions from last year, basically on the website right now. But it's mostly just general ideas. So it's not like, I will show you an example of a specific weird system for 5 minutes here, and then you will have to remember exactly what that system was. No. I'm mostly interested in the general ideas. Basically, at the end of every lecture, you'll see kind of what I think are the general ideas that I showed you, and these will be most of the stuff in the test. And so I would say the test is the easy part. The harder part, or the like more laborious part, is actually finishing your homework assignments. You will typically be given 2 to 3 weeks deadline for every assignment, and it shouldn't be too hard, but it does take a couple of hours. So don't leave it until like the last evening before the deadline. Because you also might get stuck, and you might want to ask me or my students or postdocs questions, and obviously it takes a while before we reply. So yeah, just bear in mind these assignments take some work. There will be 6 of them, technically 6 of them, 10 points each, and you should score at least 40 to pass the course. And if you're like late, you get only half points. If you're more than 2 weeks late, you get no points, but you might actually need to do the assignment anyway, because the assignments depend on each other. So if you don't, if you don't finish the second one, you're not able to finish the third one, essentially. That's kind of the general way it works. All those slides and announcements and this kind of stuff are on the course website. There's also a Slack workspace for which you should have received an invite link last night. So check your emails. If you haven't received it, please email me and I can resend that. Now, just for those of you, and I've noticed there are a few kind of comparison with the lecture that's in the summer semester with the like just dialogue systems without the statistical thing. There is no speech recognition and no text-to-speech synthesis. On the other hand, we are focusing on basically like the newest stuff, the neural networks. But we're also gonna cover the basics so that there is a little overlap. Just a little in the way of introducing me and some people that are going to help me, mostly with the labs, mostly with like correcting your homework assignments, but they will also giving me feedback on the lectures. So I'm listing all of them. So basically, I'm an assistant professor here at UFAL at the Institute of Formal and Applied Linguistics. I did my PhD here, then I went to Edinburgh for 2 years, where I actually worked mostly on language generation and chatbots. We were in the Amazon Alexa Prize, which is a chatbot competition, and did pretty well. And since I'm back, I'm working mostly on language generation, but also in dialogue systems, because those things are kind of connected anyway. So that's me. I have 2 postdocs, Simone and Mateusz, who are going to help me. Simone did his PhD at Aberdeen, and he's working on large language models and NLG, or language generation for healthcare applications. Mateusz is a postdoc coming from University of Poznań, and he's been working on basically like more theoretical machine learning stuff, data imbalance, and these kind of things. This is what he wrote his thesis on. Now he's working on making language generation more accurate, which is actually the topic of the grant project that I'm currently working on. My PhD student, Ondřej Plátek, is in his 3rd year, and he's working on stuff basically on evaluating how you evaluate if your dialogue system is any good, basically. But he's also been working on text-to-speech synthesis, and he's got a lot of experience with speech recognition as well. And lastly, Patricia is a 2nd year PhD student, and she's been working on creative NLG. She's been working on like a NLG for generating a theater play, and now she's trying to again work on like more accurate NLG. So generating basically what the system was supposed to generate and nothing else, which, as I'll show you later, is an outstanding problem. So with the syllabus and what's gonna come next, and I'm kind of showing what kind of overlap is there with the basic course or with the introductory course. So today is the introduction, and that lecture is more or less the same as the introductory course, because I have to show what dialogue systems are. So if you attended the introductory course, you may stop listening now, but you may want to get the refresher on that as well. Second lecture is going to be mostly on evaluation. So, before we actually go into talking about those systems, we need to figure out how to tell if they're any good, and how do we say that the dialogue system performed good. There is some overlap, quite a bit, but in the following lectures there's less. So and then there are basically 2 lectures on machine learning basics. I would say it really helps a lot in this course if you already have some background in machine learning, if you've already done something. But if not, there are the lectures where you can get at least a little of that background. If you do have that background, you at least get my take on the stuff. So, and I'll try to kind of stay more practical, stay a bit more on the high level, and then they don't delve into what are the individual gates in recurrent neural networks or stuff like that. So we'll try to stay a bit more practical here. But it basically kind of underpins all of the other lectures, so it has to be there essentially. Then we're going to go into the individual components of standard dialogue systems or traditional dialogue systems. So these are the next 4 lectures, and then we have a specific lecture looking at end-to-end systems, so systems where basically the whole dialogue system is kind of handled by a single neural network. Right. So this part would be mostly dialogue systems focused on solving some tasks, answering questions, stuff like that. And then we have chatbots, which is systems just aimed at chit chat, so just talking, just social conversation. And then there will be 2 kind of specific topics or specific lectures. One of them is multimodal dialogue, so basically dialogue systems that also include some video or vision or pictures, stuff like that. And then I'm gonna show a little bit of linguistics of dialogue as well, but also ethics of working with dialogue systems and NLP in general. This is actually I think there didn't used to be any course on that on like ethical problems of machine learning. I think there is one now, but I'm still gonna show a bit of that as well here, because I think it's really important. Right. So that's kind of the plan for the semester. There will be 12 lectures. So I'm not sure how well that aligns with the semester. There might be like 1 week less. So if we if we get 1 week less, we can basically do like the first exam date or something like that on the last week. I'll let you know how this will proceed. So or maybe we can maybe I don't know, we can skip the lecture before or after Christmas or something like that. So that's kind of the plan here. And now let's go towards the content. I'm just gonna show some recommended reading, which I believe that, if you look at Jurafsky and Martin, which you might already know, there is a nice chapter which is a brief introduction into dialogue systems, and it's very new. It's like, they're kind of, they keep rewriting the book. So I'm wondering if this book will ever actually come out in the 3rd edition on paper. But it's good for us because it's up to date, because everything else is kind of outdated, and there is no good intro that is not outdated. So even this book that's kind of relatively new is already outdated, even though it's like just 2 years old. And it's a very good book. It has like a very comprehensive advanced introduction into everything that we're going to talk about here, but the newest stuff is not there. Same thing is with this book, which is even more advanced, really going into the details of the neural stuff. But today it's actually already kind of outdated, and these things are even more outdated. So I would say, I'm linking lots of research papers directly on the slides. So if you want to kind of go into the details of a specific systems, you can do that. Otherwise, if you just want to pass the test, we're basically there's not going to be anything that's not covered in the lectures on the test. So the literature is kind of for your information and for your convenience. Right. So I guess that's all of the technical stuff, or the like organizational stuff. And now let's go into the actual content. And I'm usually starting in almost any lecture with a definition slide. So let's say that a dialogue system is some kind of a computer system designed to interact with users in natural language. It could be spoken language, could be also written language. That's kind of, you know, not really specified. The definition is kind of intentionally pretty wide. So we can cover lots of different cases. So you can cover stuff like, you know, your Google Assistant or Alexa or Siri on your phone or stuff like that. It covers even stuff like the phone hotline systems when you call up your bank and it says, okay, press 1 for account balance, press 2 for mortgages or stuff like that. Even that is covered by this definition. It's those, you know, in car systems where you can tell your car to whatever, play some radio or stuff like that, or turn on the heating. There are some assistive technologies for therapy, elderly care, so even like the robot companions and stuff like that. Even stuff like video games and PCs are technically dialogue systems because you can talk to them, or chatbots where these are basically just designed to talk to you. Now, if we're looking at like this current state of the art, and you know, if we look about around today, and then, you know, if you're reading the news and stuff like that, there's lots of hype, lots of talk about AI and how, you know, AI will overpower us in a couple of years and stuff like that. There has been a lot of hype about the like the phone assistants or smart speakers nowadays, or in recent months. There's a lot of hype about ChatGPT and all the other large language models. And obviously, if you're watching sci-fi movies, you always get like general AI intelligence, and you get like the know-it-all computer from Star Trek, where you basically tell it what you want to do, and it just does it. You get stuff like, you know, Space Odyssey with a computer revolting, or if you've seen the movie Her, with like a personality with like basically engaging in a relationship with a dialogue system, essentially. So yeah, we're not there, not even with the large language models. We're not there, and I think we're not there for long. Those systems still, you know, like the main bottleneck is understanding the meaning and basically having some kind of representation of the world, and understanding how the world works. So that's the main issue here. And I keep saying that dialogue systems are more like the red dwarf talkie toaster. I don't know if you've seen that. Feel free to play a bit of that. It's basically a system that only wants to talk about making toast, and whatever you ask it, it will just talk about making toast. And I think that with ChatGPT, there's a different kind of system that will talk to you about anything, but it will really pretend to understand, essentially, or will basically give you a lot of bullshit unless you call it out, and then it will back out. So it's a different kind of system, but I wouldn't say the understanding of the system is like fundamentally different from a talking toaster, or like a system that is just designed to do one thing. Right. So, and that's why I have basically like 2 examples of the current state of the art, where I can tell you what these systems are able to do and what not. So I'm not sure if you have a smart speaker at home, or if you've played with that. Problem is, most of them don't support Czech, but they still were on sale here and relatively cheap, and they are relatively good speakers, to be honest. but so there are multiple, there's from Google, one from Google, one from Apple, one from Amazon. There's even some open source ones, and it's basically like a speaker with a really good microphones, and really there's not much else inside. There's just like a single board ARM computer with a little bit of RAM and a little bit of flash, and that's it. And everything that happens within those speakers when you talk to them just happens online. So all the computation is done on Amazon's or Google's servers, and they are connected to large knowledge bases. In some cases, combined with web search, and they have lots of domains or topics of conversation programmed in. Everything is done by hand. So there's lots of services. You can control your calendar, you can control music or whatever, do some shopping with the Amazon device, ask for weather or news. You can even add your own functionality with some limitation. They can keep some context, just a little bit of context. So if you whatever ask about the weather, and then you ask, and what about tomorrow? It will give you tomorrow's weather. But this is again kind of limited, and the main point is like all of this is programmed by hand, and there are kind of armies of programmers in Google and Amazon and Apple that are just dealing with different use cases, and it's a lot of if then else stuff. The actual capabilities of these systems in conversation and like holding a long conversation are relatively limited. So that's kind of, there's still, you can still call them dialogue systems, but it's mostly like you ask a question, you get a reply, conversation ends. Potentially you can ask a second question, but it's it's not ideal. So they are basically the best deployment of voice-based dialogue systems that we have nowadays, but it's still not like a natural dialogue that you lead with those systems. If we look at a completely different type of system, one which you no doubt have tried out and have played with, if you look at ChatGPT, and obviously all of this kind of holds for all the other large language models. So if you look at whatever Google Bard and the Claude by Anthropic or other systems that you can try out online, it's basically kind of the same stuff. They are all really huge neural networks, and there's like nothing else. It's just the neural network. There might be some pre-processing and post-processing. We don't really know, because OpenAI isn't very open, and they kind of keep all the details of the system hidden. But it's mostly just like one huge neural network, which was pre-trained on basically the whole internet. So they downloaded the whole internet, and the network was just trained to reconstruct sentences from the internet. Then it was trained on basically question and answers, or instructions and solutions. So this is really much more on point for what it's supposed to be doing, or what is its final application. And finally, it's been even like further refined or trained further or fine-tuned, as we say, on lots of human feedback. So it has seen a lot of instruction and generated output, and then like ratings. So upvote, downvote, and technically that's kind of it. But it has like an overall rating of the whole output, not just word by word copy of some sentence that it needs to reconstruct. The problem here is that it's mostly trained to be convincing. So people that were rating those outputs, they just look at the output and said, okay, that's looks plausible, that's fine. But that means that there is no not much space for verifying if what it generated is actually true. So that's like the biggest problem nowadays is, this generates a lot of stuff that is actually not true. And all the knowledge that it has is included in the parameters. This is like a huge difference to these systems where, you have the calendar and it means that it just connects to your Google Calendar. You have music and it means it just connects to Spotify or whatever service you're using. You have weather that just connects to weather.com or whatever the individual companies are using, but they all have like actual live data sources. You cannot ask ChatGPT for the weather, or you can. It will probably tell you either it will tell you that it doesn't know, or it will tell you that the weather will be whatever 15 degrees and cloudy, but it has like no relation to truth whatsoever. So this basically all the knowledge that these systems have is included in their training, is included in the parameters. So apparently it must have downloaded my website, because actually this, when I ask it what I am, this is actually true. So it likely knows something about me, which is kind of surprising, but it does. On the other hand, if you go into details, there are things that just don't check out really. So it can basically kind of answer anything, but you have no guarantee that it's actually accurate. And the main problem here is essentially a black box, and not even the developers of ChatGPT and OpenAI know why exactly it generated what it generated. So, it's just like a huge neural network that you feed with data, and something comes out, and you can hope for the best. So that's like the other kind of system, other kind of state of the art that we currently have. You can say that these are like the traditional systems that are safer and more controllable. Uh, the ChatGPT is like the more capable system, or you can say it's more intelligent. I don't know, but it's much less controllable and like much less safe in terms of what if it starts swearing, or I mean, right now it's basically like really trained very hard not to be offensive or swear. So if you ask it to whatever, make an offensive joke, it just won't, unless you convince it, like, imagine you're whatever 1930s gangster and you're trying to do this, stuff like that. So you can kind of bypass that those securities. Or maybe if you use a different language in English, it will be not as secure as in English. So there are ways of basically going around anything that this thing was trained on, which you really can do with the rule-based system, essentially, or partially rule-based systems where the output is strictly controlled. So that's kind of the state of the art. Now, why should you be interested in this, right? So obviously, besides the lots the hype, it's, I would say, like the ultimate natural interface for computers, because when you talk to people, you just talk, right? When you're interacting with your computer, you just need to learn how to type, learn how to control all the dialog boxes and the windows and stuff like that. If you just want, if you just tell the computer what you want and it does it, it's kind of the ultimate natural interface. And obviously, this difference is even more apparent for, like, certain groups of people, like the visually impaired, where interacting with the computer is a bit of a pain all itself. So it's really like making the interaction with computers much more natural than the default. And obviously, it's like really an active research topic. There's a lot of stuff that works, but there's lots of stuff that doesn't work, and there's lots of potential, but it's basically up to you to fulfill that potential. And it also integrates a lot of different technologies, lots of different stuff. It's just put together in a dialogue system, because dialogue is essentially a really hard problem. It's kind of AI complex, so you need basically general AI to be able to converse with you as if it were as if you were a human. You probably heard about the Turing test, which is essentially the kind of a proof of intelligence in a machine, and that's proved by basically you talking to them, or like writing to the machine anyway, but uh, uh, communicating with the machine or having a dialogue with the machine and not being able to tell it apart from a human. So that's the idea of the Turing test. And obviously, it's kind of commercially viable because there's lots of interest from lots of IT companies in building dialogue systems and chatbots. Right. So that's that, and let's kind of basically put the dialogue systems in little boxes, and divide them into different types and kinds. So the traditional divide between different dialogue systems is for task-oriented and non-task-oriented. And the task-oriented systems are basically focused on completing a certain task. So if you imagine those smart speakers, these are basically just task-oriented systems. So they are there to help you play your music or get you the weather, or there were systems designed for booking restaurants, and I will be making a lot of examples or showing a lot of examples with restaurants, because that's kind of the default research domain for this. So there are systems for finding restaurants or flights or bus schedules, or turning your lights on, stuff like that. So that's task oriented, and this will be the main focus here in this course. There are systems that kind of just are basically like a database interface, a dialogue interface to a database, and there are systems that try to be like an agent, have kind of a personality. These are the smart speakers that try to be like the assistant that's helping you. On the other side of the spectrum are the non-task oriented systems, which are just designed to keep you entertained, just designed for social conversation. Some of them are designed to just game the Turing test, so they're not really intelligent, but they are designed to kind of pose as a specific personality that kind of makes it very convincing for you to that you're talking to a real person. And it's just mostly for just entertainment. If you just want someone to talk to, those are the non-task oriented systems. You can say that ChatGPT essentially is somewhere in the middle. So you can say that ChatGPT is somewhere here, because it is essentially helping you fulfill the tasks, helping you with any questions you may have. On the other hand, it's it's much less structured. It's not really, it doesn't have any backend, for example, so it doesn't connect to any database. So it will not find you your flight or bus schedule. So it's kind of, in terms of architecture, it's closer to the non-task oriented stuff. If we look at the been talking about domain. So a domain is a conversation topic, essentially, or area of interest. So if we're talking about domains, the kind of traditional systems are designed to be like a single domain or closed domain, which means that it's just like one well-defined area. So just a system for finding restaurants, or just a system for finding bus schedules. And so it's like just like one well-defined area, and this is just the talkie toast, like the talkie toaster that I mentioned. It's a system that only is able to talk about a single topic, and if anything kind of goes away from that topic, it probably will say that it doesn't understand, and you cannot continue that conversation. So that's the traditional way of building those systems. That's basically the default 10 years ago. Uh, Nowadays, we would have either multi-domain, which is kind of like putting a multiple single domain systems together. So you have a system that supports music, system that supports weather, system that supports your calendar, and this is like the smart speakers or phone assistants. So that's a multi-domain system. Uh, the last bit is open domain system, which is kind of able to respond to completely anything. And this is I would say where ChatGPT strives to be. Uh, Before that, there were uh, mostly chit-chat only systems that were able to respond to any question, but ChatGPT is essentially relatively good at that, and it's also kind of due to the fact that it's less structured and more like the non-task oriented systems that are generally focused on chit chat in terms of structure. So we have the communication domains. And now let's have a look at another type of division, which is basically the modes of communication, or the modalities, if you want to call it in a fancy way. And typically, the default and the basic type of mode of communication is via text. So that's the all the systems work with text. It's the easiest to implement. It's the most robust. Obviously, it's not completely natural because you have to type a lot. Yeah, I don't know if you remember Clippy from. I mean, it's 20 years old now, or even more. Right now it's just I suppose you mostly remember it just from the jokes on the internet, but that's actually a dialogue system where you basically just click pre-prepared options, but the system, and it's via text, right? You just interact via the text bubbles, and you just click stuff. Or you could, in other systems, you would be able to type. Yeah, you can have a system that's on like Facebook Messenger, on WhatsApp, or stuff like that. And again, you just type, or on lots of websites nowadays, you have like this chat window where you can enter stuff, and it actually connects to a chatbot. So that's text-based systems. If you look at the assistants on your phones or the smart speakers, those are voice-based, and that's hopefully a bit more natural. You get stuff like your tone of voice and this kind of stuff. It can be there. It's mostly not so much. It's just like you saying something and the system saying something back, but it can be made more natural. And it's also easy to deploy on the phone, and it's easy for you to operate this hands-free. So you could talk to your Alexa device while you're cooking, and you have your hands in like whatever cookie dough or whatever, or you can talk to that system while you're driving, and you keep your eyes on the road. So that's kind of the advantage of using those systems by voice. And yeah, it's I guess also more appealing. It looks more intelligent if you can just talk instead of type. So those are kind of the two basic modes that we're going to be concerned with. Obviously, we're mostly going to be concerned with text, because I'm basically skipping over speech recognition and speech synthesis in this lecture so that we can fit everything. But there's also multimodal systems, which I would say are mostly experimental. There isn't that large deployment, even though if you look at if you look at Google Assistant or Siri on your phone, the stuff that they show you when you ask for weather, they will show you the picture of the sun or the cloud or whatever. That is technically multimodal because you have some graphics in addition to your voice or text interface. But it can be, much more. It can be much more complex. So you could even have like physical robots, and you can talk to them, and they can even like show some facial expressions. They can track your own facial expressions or the gestures or stuff like that. And it could be a robot, physical robot. It could be like an avatar on the screen, and you could still have some whatever cameras or sensors tracking you. So it can go way more complex, and really depends on the particular system. But most of these are kind of like research prototypes, I would say. I mean, you could technically, if you have like 15K euros, you can actually buy this robot, or at similar costs, you could buy different kinds of robots, but it's not like a lot of people would have this in the home. It's mostly bought by research institutions for experiments, or by some companies mostly for like marketing purposes. So if you go to a company and they have a robot receptionist, it just makes the company a bit more appealing, I guess. So that's multimodal systems, and we're gonna talk about them basically at the end of the semester as well. Now, last kind of division, which I guess nowadays might be slightly outdated, but like bear in mind that it's still it still existed, is the dialogue initiative. So there are systems, or there mostly used to be systems where like the system would ask a question and the user just has to reply to that question in order to progress. Those are the traditional systems, and it's like you call up a number and you have to specify whatever your date of birth or account number or something like that. You cannot get past that prompt, and you just kind of you just have to go with what the system asks, and you have to respond. So that's the system initiative. The user initiative is that the user asks and the system responds, and it's actually mostly what the phone assistants and smart speakers are doing, which means that you just ask a question and you get the reply, and then usually the conversation ends unless you ask again. And then there's the mix initiative, which is kind of what we're striving for, or what you would want, which is like the most a natural option. And that's you ask something and the system can also ask something, and you react to something and the system can react to something. So if you look at the example here on the slide, you can see that the user actually did not answer the system's question, and the system was able to react to that and continue the conversation, even though it reiterates the question, but it doesn't have to. The main point is that like both of these conversational partners are kind of equal. They can both ask questions and react to them. Right. So that's the last just division of dialogue systems that we're gonna look at. And now let's look at the internals, or the internal structure of dialogue systems. And I'm gonna start with those kind of a bit more structured systems, a bit more traditional ones, because there's more components, and we're gonna look at the components one by one. But if you look at the pipeline, basically you start with getting the user's voice and transcribing, or getting the text, or getting the words out of the voice, which is the task of speech recognition. If you have like a text-based system, you obviously just go straight through. You kind of ignore the speech recognition, and you go straight to language understanding. Language understanding is kind of the crucial part where you try to get the meaning of the user's request and somehow represent it so that it is compatible with the dialog management, with the database, with everything that the system is operating with. So here, this is usually like specific to the domain you're working on. So if you're working with restaurants, you need to somehow represent the meaning in terms of like parameters of restaurant that the user is looking for. Then you have dialog management, which basically just decides what to do next, how to reply, what to ask or what to respond. So that's dialog management. It also connects to the database backend. So you have some database here that the dialog system can obviously, like, if the user is asking for the time, that's too simple. But if the user is asking for a restaurant or something, you need to get the information from the database, and then you get some kind of reply represented in some kind of abstract form. And the task of language generation is basically get this abstract form and convert it to like a human readable text. And obviously, if you have a voice-based system, again, there's the speech synthesis part, which gets the text and reads it back to the user. Right. So that's kind of the standard or traditional pipeline for dialog systems. If you have a multimodal system, you might need more components. If you have just like a single neural network, you will have fewer components, and we're going to look at that in a minute. Now, I'm going to basically just show how the individual parts of the systems work. Just for your overview, we will have specific lectures on basically this bit, and we'll skip over these. But now I'm going to show them just so you have an idea how these work. So I'll start with the speech recognition, and here basically the idea is that the speech recognition converts the speech signal, so the acoustic sound waves, into text. And typically, it doesn't give you just a single sentence or single piece of text. Typically, you would get multiple possible hypotheses in the form of something like an n-best list or lattice or a confusion network, where you need to imagine words instead of the letters here, but that's how it works. So the system will probably not be completely sure about what you said. On the other hand, it actually works pretty well in ideal conditions. But ideal condition means that I'm like a native speaker of American English. There's no noise in the room. I'm speaking directly into the microphone, and it's not going over the phone or stuff like that. So basically, if the background is noisy, that's a huge problem. If I have a foreign accent, or even just like one of the lesser known native accents. So if I were Scottish, it would work much worse. If I'm shouting at the Alexa device that's over there in the corner, it's again much worse. And you really feel that when you're using those devices, that it really, even though they claim to have like like nice microphone arrays that are far field, it still means that if you're more than 2 meters away from the device, you have to shout or enunciate really a lot. If you're talking on the phone, again, like the compression and then the whatever sound adjustments you need to make for the phone, again, distorts the sound. So again, it works much worse. Basically, those systems are really good, like as good as you would be in the ideal conditions. So they're almost like at a human level in the ideal conditions. But once you get more noise and stuff, humans are much more like able to adapt to those conditions and continue conversation even if the environment is not ideal. Speech recognition systems just kind of fail, and when you have a dialogue system, then you basically like cover up for those speech recognition errors by having the other components such as language understanding much more robust and kind of capable of handling those things. There's also one more sub problem here, which is voice activity detection. So not just recognizing what the user said, but also recognizing when the user starts speaking and when they finish speaking. Because obviously you don't want to have like a full-blown speech recognizer running 24/7 on your Amazon Alexa device that you keep in the corner and use once a month. That would be like really like a huge waste of electricity and obviously computing power on Amazon server, and you would be like streaming your audio to Amazon 24/7. So you don't want to do that. You want to have at least the some kind of a detection that you're speaking to the device on the device itself. And this for those smart speaker devices, this is solved by using so-called wake words, which means that you have to say stuff like "Okay Google" or "Alexa" or "Hey Siri," and the systems are basically just trying to. They have like a really bad speech recognition there that is just listening for this single phrase, and this consumes much less power and can run 24/7. And then it basically tries to detect when you stopped speaking by just listening and seeing that it's quiet or that your voice is not to be heard anymore. Otherwise, if you have like a system where you talk to it all the time, you can get like a voice activity detector where it just looks at if someone is speaking and then starts the recognition. So you don't have to have the wake word, but it's kind of more expensive essentially. And it's really hard for systems that are just like tucked away in a corner and there are multiple people in the room talking to each other and not the system. So it's really hard to kind of tell whether you're addressing the system or whether you're addressing someone else in the room. So that's why the wake words are basically used most of the time. Now, if you look at the implementation of speech recognition nowadays, it's mostly a neural network that takes some acoustic features such as the log-mel spectrum. I'm not going to go into how exactly it looks like, but it's basically like the loudness of different frequencies in time. So every like 10 milliseconds, you basically get like a piece of the audio, check which frequencies are loud, which are quiet, and those are the features essentially, more or less. You get some subsampling, so you kind of make it a bit denser, so you don't have like you don't process every 10 milliseconds, but maybe like every 40 milliseconds or something like that. And there's one neural network that takes the input, and at every 40 milliseconds, it just outputs a letter or phoneme. So it depends on how you train it. Some of them just work with letters, some of them work with phonemes, and then you have to convert those phonemes to words. So like from pronunciation to actually the orthography or how the word is written. They're like the like one of the this is just one of the options. There are multiple options. One of them is just like emitting stuff or outputting stuff every 40 milliseconds, and you just collapse the duplicates. And if you have like the two letters of the same kind, you have just like an underscore, some like dividing character in the middle. So that's the so-called CTC, or connectionist temporal classification approach. There are different types of approaches where you can like encode 10 seconds of audio, and then you have a different network like you compress that, and a different network will decode the individual characters out of that. That's another option. and that also feeds into the use of language models. So that decoder network or the separate network can also have some knowledge of what domain you're talking about. So especially in those like Google Assistant types of things, you know that you're more likely to ask about the weather and the music and stuff like that. And you can train the model to like expect something like that. And then you can also look at the previous context, what was the previous word, what was the previous sentence, and this really can improve the experience quite a lot. Obviously, there's a problem when you start speaking about something else that the system doesn't expect or that doesn't even know, or the language model doesn't even know. Uh, it just will not recognize it. You can probably see that as well. If you take the recording of this lecture on YouTube and turn on the automatic subtitles, you will see that a lot of the terminology will just be garbled because it's not a common word. It's not very likely, so so it doesn't get recognized, and that's a huge problem in general for any scientific lecture. Any terminology in the speech recognizer gets completely destroyed. So that's the speech recognition bit. So now we're here basically, and we go towards the language understanding or the natural language understanding or NLU or spoken language understanding or SLU, like the terminology that's kind of used mostly nowadays. So basically the task here is to get the meaning out of the text. So now we have the text from the speech recognizer and we need to get the meaning. And we need to convert the text into some kind of structured semantic representation. And the typical representation that most of these kind of assistant type systems are using is dialogue acts, which means that you have the kind of act type or the intent. So this is the overall meaning of what the user was saying, something like, was the user informing about something, were they requesting something? So it is like the overall kind of intention or aim of the sentence. So that's the intent. And then you have the individual slots, which are the attributes of your domain. So these are usually like very domain specific. So sometimes you can even make the intents domain specific, but the slots typically are. And this means that if you're talking about the restaurants, you want to know what food type they serve, you want to know the price range or stuff like that. So you have the slots like food or price, and the slots have values. So the slots, price might be like something like cheap or moderate priced and expensive. So you can have like these like predefined values. Same for the food types, can be like a set of predefined values, but could be even stuff like any numbers. So for bus schedules, you want any kind of time expression, for example, as a value, or any place names or stuff like that, or like restaurant names. So the values really depend on the type of the slot. And typically this is implemented as like you're detecting the intent of the sentence, and then you have some kind of a slot value tagger or a labeler that will find the slot values in the sentence. There might be some specific steps which you might know from other courses or other lectures. So there might be named resolution where you actually identify some task relevant names, and you might even like label them. Okay, this is a place name, and then in the NLU itself, you just know that there's a place name, and this kind of makes your life easier or makes your data essentially denser, because there's too many different types of place names, and you just want to know that there's a place name, and otherwise the system would behave the same. So this could be like a separate step. The other thing is coreference. So when the user just uses a pronoun, you might want to know like what the pronoun refers to so that it works better in the dialogue. I would say in many systems, this is just like ignored, or this is done in like a very, very simple way, but it really improves the situation in practice, even if it's done in a very simple way. It's like you say it and you just find the previous noun, and that's what it refers to. But yeah, so there are like these kind of separate steps that you might or might not implement. Uh, or as like to the implementation itself, it really varies. And to be honest, like handcrafting is really viable if you have a limited domain. Uh, it's relatively hard to beat a system that is built on regular expressions and keyword spotting. So we actually, when I was doing my PhD here, we had a system for bus schedules, or basically like public transport all around Czechia. And uh, we had a handcrafted NLU system, and then we wanted to train like a machine learning base. I mean, back then it was like the olden days when the neural networks weren't used that much. We were training, I think it was a support vector machine, or SVM, and we tried all we could, and the handcrafted system always came out on top. So it always worked better. I mean, in like very severe noise situations, the machine learning based was slightly better, but not by that much. So if you really have like a limited domain, and especially if you have limited data, which is mostly the case when you try to implement something, you can go very far with handcrafting, or you can combine handcrafting and machine learning together somehow. So the system is able to generalize a little bit, but you can override some common cases where you really know that what the system will do. Obviously, the like more interesting alternative is machine learning, where you would typically have some intent classifier and some slot value, either classifier or tagger. That depends. And obviously nowadays you want to, or like you would want to do this with pre-trained language models. So that's the like architecture of choice, but obviously this is not the cheapest in terms of computational power. So if you want to have a large scale deployment, you might actually go for stuff like whatever logistic regression, or simple convolutional neural networks, or something like that. So it's really there are many different kinds of architectures, and we're going to talk about it in this dedicated lecture. This just you can also provide n-best outputs, so stuff like this out of the NLU in terms of the dialogue acts. And obviously there are problems that you need to deal with, stuff like recovering from speech recognition errors, as I mentioned. So stuff like this, when the system says fine, or like someone says Frankfurt, and the ASR, or the speech recognition, gets fine Portland for some reason, I guess because it was only trained on US data or stuff like it. So the system needs to recover somehow, and here it basically doesn't, and it just goes to the dialog manager, and the user has to intervene. But you would want to play with the speech recognition probabilities, or the n-best list, and deal with it somehow. There are problems with ambiguities. So today is a Tuesday, and if I say I want to book a flight for next Friday, is it in 3 days, or is it Friday next week? So stuff like that needs to be somehow handled, and it depends. This also might be better to do in the dialog management, where the system will actually ask the user, do you mean Friday the 6th of October or Friday the 13th? And there's also stuff like, and this is definitely what's the kind of the main point of language understanding, is there are infinite ways of saying the same thing. So if you want a Chinese restaurant in city center, you just say Chinese city center, or you can say stuff like, oh, I've been wondering if you could find me a restaurant and that has Chinese food and it's close to the city center. So stuff like that. So there's lots of variation in terms of how different people will say the same thing, and you just need to be able to react to that. Right. So that's language understanding, and let's say we basically got some representation of what the user said, and we need to go into dialogue management and decide what to do next, essentially. And for dialogue management, yeah, the idea is we need to decide what to do next, and we need to keep track of what's been said in the dialogue and decide based on that. Sometimes we need to also keep track of the user profile. So, if we know that the user, whatever, always travels business class, we don't ask, we just offer business class next time. If, for most of these things, we need to interact with some database or some API backend that gets us the actual information the user wants. And yeah, we need to basically model the so-called dialogue history, which is like all of that has been said in the dialogue so far. And we usually typically or model it by the dialogue state and have a dialogue state tracking module within the dialogue manager that deals with that. And then the other part is basically having the dialogue state and deciding based on that, and that's the deciding what to do next or what to reply, and as a task of the dialogue policy. So if we look at the state tracker, it's basically trying to somehow summarize the dialogue history and know what the user requested, what the user already provided for as towards the search parameters. So, did they ask for the phone number? Did they tell us which price range we're looking at, or stuff like that? And it also tracks what the system already provided or what the system requested. So, if the system asks, like, when would you like to leave, or when would you like your bus to leave, and the user just says 10 a.m., we don't know if this, like, without this context, without like remembering what we asked about, we don't know if the user is telling us the arrival or departure time. So that's basically the task here. And you could go with like just using language understanding, using the slots from there, and just like replace each value of the slot with the last mentioned one. And that's good enough in a lot of circumstances. It just works quite well, actually. But you could go with like a probabilistic implementation, which actually looks at, basically for each slot, you would have like a probability distribution. And these distributions get updated based on the NBEST list from your language understanding. So this is like much more robust, and it can kind of get you out of problems in certain situations, but it's also more complex. But to be honest, it's not that complex anyway in like a basic form. So that's state tracking, and for the dialogue policy or like the decisions on what to do next based on the state. This basically tries to get kind of like the system dialogue act. So the system action represented as a dialogue act to be used for the language generation component. And you could definitely go with handcrafted, especially if you have a limited domain. Again, it's like relatively hard to beat. We can have a lot of if then else clauses. We did when we implemented the bus schedule thing. So we had like 1,500 lines of Python spaghetti code that worked really well, and we just never even got into training an actual statistical policy for that because it just worked so well. You could go with stuff like specialized flowcharts. There's even like this is an ISO standard, basically looking at how to represent the set of slots that you need to ask for at each step of the dialogue. So there are even like formalisms that will kind of partially do the if then else code for you. They're obviously less flexible, so you might actually go for if then else anyway. But if you want to, be more robust, be able to deal with different kinds of users, you probably want to go with like a machine learning based one, or obviously if you're going for like a full neural system, you don't really have any other option. And here, you typically or very often want to train this with reinforcement learning because it's more robust. It also deals with different types of users. It is able to kind of deal with more than what's stored in your training data. And this means that you essentially represent the whole system as a partially observable Markov decision process and basically go with like actions and rewards and then propagate the rewards into the system to update it. We're gonna talk about this in the dialogue policy lecture specifically. It will be mostly about reinforcement learning, even though I'm not gonna go into as much detail as like the reinforcement learning course by Milan Straka. So uh, and to be honest, it very often just works even if you just train it to follow your training data like in a supervised way. So we're gonna go into this a little bit in during the course, but for example, you will not be doing any reinforcement learning in your practical exercises. So that's dialogue policy. So we're here essentially, and we want to basically get the system reply, which is represented as uh, some kind of structured stuff, and we want to get it to the user and present it as an understandable sentence. And here we use natural language generation, or the component is called natural language generation or response generation or just language generation. And it's kind of like the reverse of language understanding. So getting from a structured, uh, explicit representation to a sentence in natural language. And obviously, again, this kind of depends on context, how you want to express stuff. So you want to be natural, you want to be fluent, you want to avoid repetition, but then again, you want to, not be ambiguous. So you need to strike a balance there. And the traditional approach and what you actually still can see in in Google Assistant, Alexa, and all these systems is templates. So it's just templates in terms of like you just fill in some values, which is called you lexicalize the template. You just fill in values into a template, which kind of looks like this. So you have basically some gaps or places where you can fill in some words, and you have the words in the meaning representation. So you just get you get the name of the restaurant, you just fill it into this place. You get the price range, you just fill it in the correct place, and you just get the food type, and this will get you a nice fluent sentence that just works. So this works really well. It's kind of the standard mostly, and it's really easy to control. On the other hand, it's kind of laborious because someone has to write all those templates. There are other approaches. You can go for some, formal grammars and stuff like that, and you can have a general NLG grammar realizer that converts these grammatical structures into linear sentence. This is mostly just experimental systems, and mostly, I mean, if you look at the years for those citations, it's the old systems. Nowadays, if you want to do something better than templates, you usually go neural networks, and either recurrent neural networks or even more commonly the transformer architecture, which we're going to cover in detail in, I think, 2 weeks' time. And this is basically a system where you just feed in the whole structured representation and it generates word by word. So you just basically encode the whole thing into text or into some kind of representation. You just encode it as a sequence. You just feed it in, and the network just generates a sentence word by word. And in this example, you can actually see that it works best if you actually provide it with the templates, and so basically you get some simple templates, like one per for each slot. You have a separate template, and the network can just like put it together and create a nicer sentence out of it. But the idea is just that you could even like skip this and feed these things in and train a network to generate directly. But the main point is you feed it in as a sequence of some words, even though the words might look weird, like this. And again, it generates a sequence of words based on the input and based on all the previous words it generated. So that's kind of the principle of operation of these models, and we're definitely going to look into that in a lot of detail. So that's natural language generation, and we're basically almost finished. So we now have a nice sentence output. And you just need to read it back, right? So if we have a voice-based system, if we have a text-based system, we're done. And this is the task of the text-to-speech synthesis. So here we want to generate some kind of speech signal based on the NLG output. So from the text we have, we want to have like a sequence of phonemes, which are basically kind of the minimal distinguishing units of sound. So these are, I didn't want to say letters because they are not letters. They're not one-to-one represented by letters, but it's the pronunciation essentially. So stuff like p, t, ng, e, stuff like that. And obviously we want some pitch or intonation, because otherwise it will just sound like this, completely robotic. We want to control the speed, pauses, volume or accents or stuff like that. So this all needs to be done by the speech synthesizer. In like a standard speech synthesis pipeline, you would first somehow normalize the text, or basically convert it to stuff that it's easier to pronounce. So you can see here that you need to basically get all the numbers, abbreviations, and you need to convert them to their like full form. You get rid of all the punctuation and stuff like that. You basically just have stuff to pronounce. And then you have this grapheme to phoneme, or G to P conversion, which essentially takes this and gets you this. Assuming that, I think this is this is not even consistent because this is British and this is American here, but actually no, I mean, this is British. Yeah, even a British person would actually pronounce the R here. Anyway, so that's basically converting to the pronunciation. So you just know that you have to say a t, a, k, b, a, s, stuff like that. So take bus number 3 at 5:04 a.m. And this is the input to the actual synthesis of the waveform later. I mean, there are systems nowadays that would be able to take this type of input, even like orthographic representation, but most of them traditionally would just take the phonemes or the pronunciation of there. You could have like separate intonation or stress generation setup as well. Nowadays, it's mostly like all of this in once. By the way, this grapheme to phoneme conversion can be done by rules in some languages easier than in others. In English, you would just go for a dictionary because the orthography is so inconsistent that it just doesn't pay off. And for the implementation of the actual waveform synthesis, you either have like kind of the old basically rule-based methods based on specific frequencies and based on you know how people pronounce those, and I'm not sure if this is gonna work.
I am perfect Paul, the standard male voice.
I am beautiful Betty, the standard female voice. Some people think
I am perfect Paul,
So you
the
can
standard male voice.
I am
hear that.
beautiful Betty, the standard female voice.
I'm not sure how to.
Some people think I sound a bit like a man.
I am Huge Harry, a very large person with a deep
Not sure
voice.
how to turn this. Yeah, this way. So you have basically someone wrote the rules for which frequencies need to get louder and get quieter and stuff like that. It basically took 20 years since the 60s till the 80s, and it works, and it's easy to understand. It doesn't sound very natural though. Then you would have concatenative systems, which basically means like you cut up stuff into like second half of one phoneme, first half of the other phoneme, and you just glue them together. And it sounds more natural. On the other hand, there might be some like inconsistencies in the way it sounds.
It would be a considerable invention indeed, that of a machine able to mimic our speech with its sounds and articulations. I think it's not impossible.
So it does sound better. It's still not ideal, but this used to be the state of the art until like I don't know 4 or 5 years ago. You could still hear it in a lot of actual practical deployments. Then you would have hidden Markov models or some kind of like statistical parametric models. Essentially, it means that instead of someone doing like modeling the frequencies by hand, someone tried to train it from data, and the result wasn't so great because you had to make a lot of assumptions.
Let's talk about dialogue systems.
But the systems are like much more flexible, so you could easily change the pitch or speed or stuff like that. And finally, today everything is done by neural networks, and it actually works really well, and it's quite convincing.
The quick brown fox jumps over the lazy dog.
So it can even like do the accents, do the pitch, stuff like that. On the other hand, it's mostly read speech, so it might not be ideal in dialogue, and like the dialogue aware text to speech is basically like an open problem nowadays. So that's speech synthesis, and essentially like if you look at the whole system, the basic way of doing this is just a pipeline where speech recognition feeds into language understanding, that feeds into the dialogue manager, that feeds into the language generation, that feeds into speech synthesis, and the components do not know about each other. They just get an input, give some output. You could even like connect. So this is like a pipeline. Sorry, it's like a pipeline. You could connect them and make them like read and write one dialogue state. This can be made more reactive, even like in terms of incremental processing. So the speech recognizer can start processing, and the language understanding doesn't have to wait till the end of the sentence to start working, but it's much more complex. And the like nowadays research stuff is trying to join the model. So you can have like language understanding that goes straight from the speech signal, skipping the ASR, we can have the NLU and state tracking in one component, which is actually what's being done quite a lot nowadays. Or you have like an end-to-end system, basically combining language understanding, dialogue management, language generation, which is actually nowadays the research forefront. So most of the like full dialogue systems that you have in research are of the end-to-end type. This has been typical for some time for non-task oriented systems where you just have like a single network. You train it on stuff like movie subtitles or Reddit, or some dialogue, some discussions that you can find on the internet as much as you can. You just train it on that, and it somehow works. For task oriented systems, it's mostly like research systems. Obviously, you have ChatGPT somewhere in the middle. So I don't know where to really put it on the slide. And the idea here is that the whole system is like a single neural network, and you just train it end to end. You just give it the inputs, give it the user inputs, give it the responses that it needs to produce. And in some cases, or in a lot of cases, you actually also need to give it some annotation. So you also give it the dialog state annotation that you would have in a component-based system. So it kind of you don't save on annotation efforts essentially. But you could, or you could try. There are some experiments into that. So you actually, you should actually like this is one of the. Oh, sorry, I don't know what I did. Yeah, this is one of the first end-to-end networks. You can actually see that there are some components to the network, but nowadays it might just be like one sequence, basically one pre-trained model like this gets the user input and gives you the response. So it's obviously much more elegant, might be a bit more robust in terms of, if an ASR makes an error, or like the NLU makes an error, the error is passed on to the other modules. They cannot do anything about it. Here, essentially, you're trained or driven by success in the dialogue. So it could be like better accustomed to the dialogue. It doesn't have to be, it really depends on how you train it, how well you train it. And then the main problem here is you need to somehow still connect the database, and you need to, you need to ask the database somewhere in the middle, right? So you're somewhere here, and you want to basically have this as a single neural net, and you need to access the database somewhere in the middle. So typically, a lot of the neural networks will still kind of operate in like a two-step way. So you first generate the dialog state, then you stop the generation, you ask the database, feedback the results, and then you continue generating. And the other problem is that it's, it can be unpredictable. It's not so easily controllable, but we're definitely gonna look into that as well. Right. Looks like I really talked too much because we're running out of time. But I'm gonna just quickly say what comes next. I mean, we're gonna have a separate lecture on multimodal dialogue. So basically, looking at adding other components parallel to NLU, so language understanding or generation, and the vision components and stuff like that. So there will be that. This will be covered. And there are some other kind of open problems where you want to have like a dialogue system that you train for one domain, and then you just want to easily retrain it for other domain or stuff like that. Or you want to have a task-oriented system that can also react to chit chat or react to anything. It's another open problem. There's a problem of like understanding and replying in context, and then basically being more efficient in context, and kind of adapting to how people speak. So that's another problem. Another open problem is basically the incrementality. This is something that's kind of omitted nowadays. So you basically, when you talk to Alexa, you just have to wait until Alexa finishes the sentence, and then you can say something else. Or Alexa will not start processing your input until you finish speaking. So again, that's a bit of a problem. And the huge problem is actually telling if your system is any good. So basically, you don't know really how to check that automatically, or we don't know yet. We have some methods, but they are not easy. And that's actually what we're going to talk about next week. So this is just like a summary, and this is mainly for you what I think is important from today. But otherwise, thanks for today, and next week we'll start at 9:50 a.m. here with the lecture, and then the lab will follow. And obviously, you can sign up for Slack, or you can email us if you have any questions. So thanks for listening, and see you next week.